Okay, so today we'll be talking about using NFAs, DFAs, and regular expressions to do scanning in a compiler. So in a compiler, NFAs, DFAs, and regular expressions are used to do scanning or lexing. And what do we mean by scanning or lexing? We mean dividing the program into tokens or lexemes or words. What do we mean by tokens or lexemes? When you have something like x 1, 2, 3 equals yy 8 in a statement, an assignment statement in a typical programming language, this statement consists of this variable, right? So the left-hand side variable, and the assignment operator, and this other variable. Or maybe let's make it more interesting, add a little bit, plus 73.9. Okay. Okay, so in this case, what we would like to do in a compiler is to divide this statement into these different tokens or lexemes. So we would like to identify this as a variable name, and this as an assignment operator, and this as another variable name, and this as an operator, the addition operator, this as a constant, and this as the end of statement indicator. Okay. Now, how do we do this? We simply, how is this done in a real compiler? People simply construct a regular expression to describe each one of these, like a variable name or identifier. There is a rule defined using regular expressions, as we will see in a minute, to define what a variable name or an identifier can consist of. A rule for an integer variable, a constant integer, or an integer constant, or a floating point constant. So this doesn't match the rule for an integer constant, it matches the rule for a floating point constant, as we will see. We will write rules for variables, integers, and floating point constants in a minute. But before we do this, let's see how things work. So we define a regular expression for each one of these different. Of course, the regular expression for these operators is trivial. And what's the regular expression for the assignment operator? Yeah, it's just the assignment operator itself. So for the assignment operator, there is a language that consists of a single string. So the language of the assignment operator is a language that has a single string in it, which is this. While the language that has all valid variable names has much more strings in it. It depends on whether you limit the length of a string or you don't limit the length of the string. If you don't limit the length of the string, then you will have an infinite number of strings in the language that has all valid variable names. And same applies to the language that has all valid integer constants or floating point constants. Okay, so let's try to write a rule for an integer constant. a regular expression rule for an integer constant. Now in this case, in compilers, when we apply this to compilers, what's going to be our alphabet? Is it going to be 0, 1? It's going to have all the characters that can appear in a valid program. So the alphabet for a given programming language is going to have every single character that is a valid character in a string in that language. So you will have the numbers 0 to 9. So you'll have maybe, okay, so sigma is going to have the set of numbers 0, 1 through 9. Union A, B through Z. Union uppercase A, uppercase B through uppercase Z. Union everything else. All the symbols like plus, minus, equal, etc. We're not going to name all of them, but every character, every valid character is going to be in this sigma. And in fact, we will use for this, for 0 to 9, we'll use this, 0 to 9. For this, and we will use for A to Z, we will use this, A to capital Z. So from lowercase a to uppercase Z means all lowercase and uppercase letters in the English alphabet. Okay? So now given this, regular expression for an integer constant, a first attempt would be something like 09 star. So any number from 0 to 9, and you repeat it as many times as you want. So this is the regular expression. But this can generate things that we don't like what? That are normally undesirable. Like the empty string. So this can generate the empty string. So in order to avoid the empty string, we will make it, we will force it to have at least one digit in it. So we can do something like 09 star. By the way, there is another way of writing 09 stars. There is a notation, the plus notation. So this is equivalent to saying 09 plus. So this is the first time I introduced this. 09 plus is, the plus is like the star, but the number of repetitions has to be at least 1. So x plus is equal to x star. So you can think of 09 plus as shorthand for 0909 star. So with the star, you can have, you can repeat 0 times, so you can have the empty string, but with the plus, you cannot have the empty string. You'll have to have at least one digit. Okay. But still, this may generate things that are not desirable, like, leading zeros, like, it will accept something like this. So what if we would like to not allow leading zeros? So leading zeros. How can you write the regular expression such that leading zeros are not allowed? What's that? Then you will not have zeros at all, right? So you want to do, okay, 1 1 through 9, then 0 through 9 star. So you're saying that the leftmost digit must be between 1 and 9. 0 cannot be the leftmost digit. And then to the right of that, you can have anything, including 0. So the 0 is allowed. But so this will will not allow leading zeros. But what's the problem with this? Yeah, you cannot have a 0, but you can add it like 0, right? So you can just do union 0. Then you can have the 0 by itself. So either a 0 by itself or a number, an integer that does not have leading zeros. So this is for integer constants. What about floating point constant? For a floating point constant, you have basically two integers and with a decimal point between them. So the floating point is like an integer dot integer. So you can use the rule for integers. So you can say, okay, a floating point constant can have 0, 9, or this whole thing. 0, 9, no, not 0, 9, 0, union 1, 9, 0, 9 star. Then there is a decimal point. And to the right of the decimal point, you can say 0, 9 star. Now here you are allowing the empty string, but the empty string to the right of the decimal point can be fine. So you can have something like x equals 5 point. By the way, here we're not we're not discussing what should be accepted and what should not. We are discussing how to write a regular expression to express the syntax of a language, of a certain language. So the language syntax is given to us. We're given a certain syntax, and our job is to write the right regular expression for that. Now, so assuming that this is acceptable, now how do we rewrite this such that the decimal point is optional? So here with this regular expression, the decimal point is mandatory. You must have a decimal point. How do we make it optional? Union with?
Just 1 through 9 and 0 through 9 star.
No, but then you will not be allowing it. You will not be allowing the decimal. We want this decimal point to be optional. So we don't want to delete it. We don't want to make it an integer. So how do you make the decimal point optional?
Well, you could add another union that just has the 1 through 9 and the 0 through 9 star. Just separate.
Okay, yeah. So you can do another union this whole thing with this 0 union 1 9 0 9 star. You can do this, but you can also do, well, this is okay. So this is you can do this, but it will be easier to just or this thing with epsilon. So you can do this thing or epsilon. But is this what I want to do? Does this give me what I want? Does this regular expression give me what I'm trying to do? Why not? What's that?
Some parentheses.
Yeah, I need parentheses because according to the precedence rules, this concatenation will have higher precedence than the union. So this concatenation between this whole thing will be done before the union, and this is not what I want. So I need to use parentheses so that in order to get what I want, and to use parentheses to override the precedence rules, I'll just do this concatenated with, is this good now? No, not yet, right? Because this is concatenation. The concatenation has higher precedence than the union. So I will need this. Now, this is what I want. Okay, so make sure that you use the parentheses to get what you want. So let's now write a regular expression for a variable name or an identifier. So in a language like C, C++, or Java, what are the rules for a variable name? What's a valid variable name? Like x2 is a valid variable name, right? How about 2x? It's not a valid variable name. So then what's the rule? Letter, yes? Letter followed by any combination of letters or numbers, right? So you can say the first character must be a letter. So it's A to Z followed by A to Z or 0 to 9 star. Okay, so the first one must be a letter. Then after this, you can have as many letters or numbers. But there is another character that we can use in a variable name in C-like languages.
Underscore?
Yeah, underscore. So where can we have the underscore? Can we have it in the beginning? Yes, we can. Yeah, we can have the underscore in the. So we can have underscore x2 as a variable name. In fact, you can have the underscore by itself as a variable name. In fact, you can do integer underscore. And then you can do underscore equals underscore plus 5. How many people have done this? Yeah, I did it once because a student asked me about 7 or 8 years ago if underscore can be a valid variable name. So I tried it on I think the Visual C++ compiler, using the Visual C++ compiler. So I defined underscore as a variable name, and it accepted it, and I could add it and subtract it and do anything I wanted with it. Okay, so all right, so now to add the underscore, we can just add it. The underscore can be here or here. So I can add this union underscore. And this, the first part, I can add union underscore. So underscore can be in the beginning, or it can be repeated in the repeated part. So this part cannot have numbers. Just you cannot have numbers here. Okay, what about constant strings? Something like A, B, C, D. So the first attempt for a constant string would be sigma star, right? So there is one problem with this. What's that?
That's for the whole language is sigma.
So sigma star is like start quote or open quote, close quote. Then you can have anything, which is fine. But there is one thing that you cannot have between the start quote and end quote.
Numbers.
What's that?
A number.
No, you can have numbers. Why not? So this is a valid string. You can have numbers. The only thing that you cannot have, close quote. Yeah, you cannot close. So you cannot, because if you close it, that's going to end the string. So you need to exclude the close quote. And now to exclude it, using what we have defined, the operators that we have defined so far, you'll have to put all the valid symbols except the close. But we will introduce the complement operator. It's not a standard regular expression, so you cannot use it in standard regular expressions. But in the extended regular expressions, you can use the caret as the complement operator. So the complement of x is sigma star minus x. So now we can do anything but close quote, and this is repeated any number of times, then close. So this is anything but, so it's the complement of close quote. This is the complement. Okay, so anything but close quote, repeated as many times as you want then between these quotations. Now, what if we would like to exclude the new line? Because sometimes we don't want the new line operator to appear in the string. Yes. Now, how does this work? You know, in a compiler, you write a regular expression, but you will need an actual program that will. You need to generate an actual program that will recognize these different tokens or words. And the way this works is by using the conversion procedures that we have studied in this course. So we take a regular expression, then we use which conversion procedure converts a regular expression into an NFA? Yeah, the Thompson construction. The Thompson construction converts a regular expression into an NFA. Then we convert the NFA into a DFA. So which procedure does this conversion?
Subset.
Yeah, the subset. So now why do we want to convert it into a DFA? Because it's easier to implement as a program. The DFA is easy to implement as a program. Well, the DFA is just a lookup table. It just says, okay, if you are in state Q1 and you get symbol X, then you go to state 7. And if you get Y, you go to state 3. And if you get Z, you go to state 2. So the DFA is easy to implement. even though the NFA is easier to understand. So, or it's, you know, the regular expression is the most convenient way of expressing the rule for a given, you know, language construct, like a variable name or a constant. The regular expression is the easiest to use and to understand, but it's not the easiest to program. So that's why we convert a regular expression into an NFA, and then we convert the NFA into a DFA. And in fact, we do DFA minimization as well. So the DFA gets minimized. Minimization. And we get a minimal DFA. So for example, just to show you, you know, what the NFA for this will look like. The NFA for this will look like, this is your start state, and then you can start with either, in fact, you will start with either an underscore or A to Z, and then this takes you to another state, and then in this state, so this is Q0, and in Q1, what would you do? What should we do in Q1? So what does the star translate into? It's a loop. So just, you can have underscore union AZ or 0 to 9. Okay. So, in fact, yeah, so this is already a DFA. Yeah, but for not everything is going to be already a DFA. Like, you know, the 0 union 19 09 star. So you implement this by an NFA like epsilon epsilon. So you don't need the epsilon. Well, the standard procedure is going to give you the epsilon, but here you have either 0 or 19, and then here you get to an accept state. Here you have you go to an oh, by the way, this should be an accept state. You get to an accept state, and then 09 star. Here you should go to a trap state if you get anything. If you get any sigma, you should get to you should go to a trap state. Anyway, so I'm trying to show you how, you know, these regular expressions can be converted into NFAs or DFAs. And so this, you know, this should give you an idea about the usage of regular expressions, finite automata in doing scanning in a compiler. Now, scanning is one of the easiest stages in a compiler. The more challenging and more interesting stage is parsing, which is taking these tokens that you identify during the scanning stage and constructing statements out of them or sentences. So you can think of the tokens that you recognize during the scanning as words. Then in parsing, you take the words and you construct what? Sentences. Sentences like statements. So this is, x12 equals yy3. So this is a statement that consists of words or tokens that were recognized during the scanning. So this comes from the scanning. This gets recognized by the scanner as one token or word. And this is another token. And this is a third token. So basically the tokens that get recognized during the scanning phase become the alphabets for the language that the parser is based on. So a string in the parser, on the parsing level, consists of tokens or words that get recognized during the scanning phase. Okay? So from the parser's point of view, this will be one piece recognized as a variable or identifier. And this is what a second piece, a third piece, a fourth piece. Okay, so at the parsing level, the tokens that are recognized by the scanner become the alphabets of the language that the parser works with, and we will see the parsing, how parsing works, or we'll get an idea about parsing after we learn context-free grammars.